Hi, today we are looking at Newton's method as well as the L'Hopital's rule. So we'll start with Newton's method. So with Newton's method, we utilize it to approximate the zeros or roots of a function by repeatedly finding the x-intercepts of tangent lines on original function. So we will essentially be utilizing this equation over and over, where we've got x subscript n plus 1 equals x subscript n minus f of x subscript n over f prime x subscript n, where n starts at 1 and gradually increases by 1 each time, always being an integer. So I'll show you what that means graphically. So graphically, for example, we might estimate that we have an x-intercept at this value here, which we will call x1. Now that as a coordinate here, that when we plug in would give us f of x1. Now what we would do at this point is take a tangent line to this point, and what we'll find is when we do the tangent line, our tangent line crosses our x-axis closer than our original point was to the x-axis, to where we had our x-intercept here. Now this point that we just found, where it crosses here, we'll call x2, and we will go up to our graph. We know this coordinate is x2, and we will substitute it into our function to get the y value here, so f of x2. What we do then is repeat the process of drawing another tangent line. So we can see that we have another tangent line, and this one's x-intercept is even closer to our original x-intercept. So this point here we'll call x3. So if we go up, its location is x3, comma, f of x3. And we'll once again draw in a tangent line. And you'll find every single time we do this, we're getting closer and closer to the actual x-intercept. Now, by the time we do this 5 or 6 times, we are usually very, very close to that x-intercept. So we'll do an example where we utilize this. So we want to use Newton's method to approximate the solution for the equation x cubed plus x minus 1 equals 0, starting with an x value of 1, and we want to give the first 4 iterations. Now, if it's asking about first 4 iterations, we're not counting the initial value we're starting with. So we essentially want to know what x5 is. So I'd start by writing out our equation. So we've got f of x equals x cubed plus x minus 1, which makes f prime of x 3x squared plus 1. Now we're starting out with x1 is 1. So to get x2, that's going to equal x1 minus f of x1 over f prime of x1. So if we substitute our values in, we get 1 minus, well, we know that we have a fraction here, which is our f of x1, so we can fill in this with our value of x1. So we've got 1 cubed plus 1 minus 1 over 3 times 1 squared, which is our f prime, plus 1. Now in this case, that's 1 minus 1 quarter, which is 3 quarters. Now, like I mentioned, often we are solving to 5 or 6 decimal places, so we will often quickly move away from fractions because we'll often have values that don't work out to nice clean fractions. So if that's x2, x3 would be x2 minus f of x2 over f prime of x2. So that's going to be 3 quarters minus 3 quarters cubed plus 3 quarters minus 1 all over 3 times 3 quarters squared plus 1. Now this works out to 0.6860. Now in my calculator, I'll keep more decimal places than that, and I'll just use my calculator's answer function each time I'm substituting in, so I'm not losing decimal places. So that gives me x4 is equal to x cubed minus f of x cubed, or sorry, not x cubed, x subscript 3, of f prime of x subscript 3. So we now have 0.6860 minus 0.6860 cubed plus 0.6860 minus 1 all over 3 times 0.6860 squared plus 1. And that gives us 0.6823. Now our x5 would be x4 minus f of x4 over f prime of x4, which gives us 0.682 minus 0.682 cubed plus 0.682 minus 1 over 3 times 0.682 squared plus 1, and that's giving us 0.6823. So we are essentially incredibly close, and we can essentially say, therefore, x equals 0.6823. Okay, on to L'Hopital's rule. Now, this is used for our basic indeterminate forms of 0 over 0 or infinity over infinity when we're looking for limits. So if our limit of f of x as x goes to a, or equals our limit of g of x as x goes to a equals 0, or our limit of f of x as x goes to a of our limit of g of x as x goes to a is plus or minus infinity, then our limit of f of x over g of x as x goes to a is equal to our limit of our derivative of f of x over our derivative of g of x as x goes to a. So we will do a couple examples to see what this. So first one, we've got our limit as we approach 2 from x, and we've given x squared minus 4 over x cubed minus 8. Now, from looking at this, we can see essentially that means that this goes to 0, this goes to 0. So that would be our limit as we go 0 and 0 numerator and denominator. So what that means, based on that previous page, is what we can do is take the derivative of both our numerator and denominator. So this will equal our limit as x goes to 2 of the derivative of the numerator, which is going to be 2x, over the derivative of our denominator, which would be 3x squared. Now, in this case, we're no longer going to 0 for either one of them. So that would be 2 times 2 over 3 times 2 squared. And that gives us a limit of 1/3. Next, we have our limit as x goes to infinity of 2x squared minus 1 over 5x squared plus 3. So once again, we've got a limit that's going to infinity over a limit that goes to infinity. So we'll take the derivative of both the numerator and denominator. So we've got our limit as x goes to infinity of 4x over 10x plus 3. Now, from looking at this, we can see that that would just equal 4 over 10, which simplifies to 2 over 5. Next, we have our, I think we just did that one, yeah. So at this point, we'll go on to practice work. Let's show writing a different limit here. So we'll do our limit as x goes to 0 of e to the x minus 1 over sine of 2x. Because we know as x goes to 0, this goes to 1, so that gives us 0 in our numerator. And we know sine of 0 is also equal to 0. So we'll take the derivative of our numerator and denominator. So we've got our limit as x goes to 0 of e to the x over our derivative of sine 2x would be 2 cos 2x, which if we substitute 0 in would give us 1 over 2 times cos of 0. Cos of 0 is 1, so 2 times 1, so 1/2.